Hi, everyone. So I'm Kimon, and I'm going to talk about learnability of algorithms. I'm going to present two results. So one is a hardness result, and the other one is a positive result based on the papers that are listed here. So the first paper is basically a result about shuffling machines. So we show that there exists a class of machines that they do shuffling. That if you try to learn those machines end to end, then that's going to be statistically hard. On the other hand, if we try to do step-by-step learning with gradient descent, this can be efficient. And not only that, we'll see that it can also be exact in the sense that the model can learn to execute algorithms and instructions without making any error. One kind of initial benchmark that people used for this kind of topic is arithmetic. So people try to figure out if they can train models, neural networks to execute, like to do arithmetic. Not one of the first papers, kind of probably not the first one, but kind of indicated the importance of this kind of reasoning is by founders of OpenAI from 2014. And even today, we see like a lot of researchers, they're trying to figure out empirically if large language models, they can do arithmetic. The reason that we care about this kind of problems like arithmetic is, although for humans it might be easy since we learn this kind of tasks at school, for machines it's kind of difficult because we have to train the model to learn a lot of non-trivial concepts. We have to learn numerical operations, if statements, composition of those operations, and it's hard, right? So we can see that even very large language models, they still make mistakes when it comes to this particular task. So what do I mean by algorithms, right? So I'm going to use a computational model, which is a bit old, but starts to become relevant again, which is semi-automata. It's a very simple model. So we have the input data, and we have a function. This is like a processor, takes the data as input, and we also have an input sequence of instructions. So the function f takes as input those two types of data and gives an output back. And then what we do is we take the output and we give it back to the function f as input. And we do this iteratively like an algorithm. Now, this function can represent a lot of things. It can represent state transition function, discrete rules, conditional branching, and compositions of the above. So I'm going to show some examples that are relevant to the work that I'm going to present today. Let's take, for example, shuffling, right? So the input data is a deck of cards, and we also have an input sequence of instructions. So, for example, the first instruction could be swap positions 5 and 12, and then the second instruction can be swap positions 3 and 10. And in total, there are n choose 2 instructions. Let me kind of illustrate this example. So again, we have the input data and we have the input sequence of instructions. In this case, the first instruction is swap positions 5 and 12. Second instruction is swap position 3 and 10, and so on. So now we have the function f that's going to take as input the cards and the input sequence of instructions, and it's going to try to execute them. So the first step is to take the cards as input and swap 5, 12, the instruction swap 5, 12. And then it's going to execute the instruction. It's going to swap the cards at positions 5 and 12. Then the shuffled deck of cards is going to be given again as input, and then the function f is going to take also as input the next instruction, which is swap 3 and 10, and then it's going to execute the instruction, and it's going to swap the positions. Okay, so with this model, we can actually do a lot of stuff. We can do simple machines like permuting data, comping data. We can do arithmetic. If the input state is also large enough, then we can also simulate one instruction set computers. It can be less efficient, of course, when you want to simulate a whole computer. But as we'll see later, if you do it step by step, it can actually be efficient. All right, so what's the learning setting, right? So we're going to assume we have a fixed set of discrete instructions, and we're going to have a fixed set of n discrete data. And then we're going to pick a target F star, which is unknown to the learner. The learner is basically, the goal of the learner is basically to identify F star given input-output pairs, or maybe given statistical queries, the ability to ask statistical queries about F star. And of course, we also care about computational complexity, like how many data, how many queries do we have to do in order to identify F star. Okay, let me start with the hardness result. So learning end-to-end can be hard. So what do I mean by learning end-to-end? I basically mean I have end-to-end training data. So what I give to the learner is the input starting data, basically the initial deck of cards, and the input instructions. And I only have access to the last iteration T of the target F star, right? I don't have access to intermediate steps of this process. And what do I mean by how do I learn, right? So in this particular case, the result is learning via statistical queries. So in a sense, in a similar way that humans, when they try to learn something, they might ask questions. Machines can do the same thing. In this case, we can ask, we're going to ask statistical queries. So what do I mean by that? We have the instructions and the data. I'm going to assume they follow some distribution. And then we allow the learner to submit a statistic H to an oracle, and it's going to require tolerance T. Then the oracle is basically going to take H and T, and it's going to return an approximation to the expected value of H with respect to distribution D. And the approximation is going to be up to tolerance T. Okay, so let me give you an example because this might be very vague. So gradient descent is actually an algorithm that falls into this category. So let's assume, for example, we want to minimize the expected loss. We have some data X and the output of the algorithm, and we want to minimize the expected loss. In this case, we can set H to be the gradient of the loss function, and that's going to be the gradient statistic. So then basically the oracle returns an approximation to the expected gradient up to tolerance T. Here's the hardness result. Basically, what we show is that if you have a machine that has n states, and the instruction set has size n cubed log n. So this is basically all the instructions that I can execute. The sequence of instructions can be longer. This is basically the set of instructions that the function f can execute. And then I'm going to assume that the algorithm is run for n squared log n iterations. Now you can replace theta with omega here, you can get similar result. And so if those three conditions hold, then we're going to show there exist algorithms F star, which are hard to be learned in the sense that we need super polynomial number of queries or exponentially small tolerance, as we'll see later, to be learned. Okay, so let me give you a high-level idea of the proof, right? So again, we work with a class of semi-automata, and what we're going to prove is that there exists a subclass of shuffling machines and within this subclass, there's a target that we want to identify, F star, which also represents a particular chosen shuffling machine. And the way that the learner is basically trying to identify F star is, as we said earlier, is going to submit statistical queries to the oracle, and the oracle is going to reply back. And then the learner wants to use that information, the answer from the oracle, in order to eliminate machines that are not equal to F star. So here's an example. Let's say that the learner submits a query, gets some information back, and then using that information, you can eliminate some region of the subclass of shuffling machines. And then doing a second query, we can eliminate another region. And then we can do a third query, eliminate another region. And our goal is, of course, to keep asking questions to the oracle until we're able to identify F star. The problem is that this subclass of shuffling machines is actually large. We're going to construct it such that it has n factorial machines. And the other issue is that the machines are uncorrelated. And this is very important because if I have some information about a particular machine, then this is not really useful for eliminating other machines. So that implies that we can eliminate at most polynomially many polynomially many machines per query. And since we have exponentially many machines, that's going to imply super polynomially many queries in order to identify the target machine F star. Okay, proof of sketch. I'm going to introduce again shuffling with swaps. Then we're going to create the exponential, the family, exponentially large family of shuffling machines. We're going to show that the machines are uncorrelated, which is going to imply hardness. And we're going to reduce this to a random walk and use some tools from representation theory. Okay, so let me start again, the step one by shuffling machines with swaps. We already saw an example of that. I'm just going to repeat it quickly. So initially we have a deck of cards and we have a sequence of instructions. An example can be an example of instruction can be swap positions 3 and 10, and then the machines execute the swap. And then we can have another instruction, which is swap positions 5 and 12, and then the machine executes the instruction. And in total, we have entries to swaps. Okay, so this is just a single machine, right? And I want to be able to construct a family of shuffling machines that includes exponentially many machines. So how do I do that? How do I construct exponentially many machines out of a single machine, right? So far, what we do is the function f, the machine executes all instructions that we give it. So if the first instruction is swap 5 and 12, it's going to execute it. And if the second instruction is 3 and 10, then it's going to execute that as well. Now we're going to introduce a filter around our machine. And the filter basically is going to decide if the machine is going to execute a particular input instruction or not. So here's an example. Again, we have the instruction swap 5 and 12. Now we pass it through the filter, and let's assume that the filter decides to execute the instruction. And then we go to the next instruction, which is swap 3 and 10. But now the filter decides not to execute the instruction. So how do we define such a filter? Well, we take all possible instructions that are entries to, and what we're going to do is we're going to basically flip fair coins for each instruction. Right? For each instruction, I'm going to flip a coin. And then depending on what the result of the coin is, the filter is going to decide if it's going to execute the instruction or not. So for example, if the coin is tails, then the filter does not execute the instruction. If it's heads, then it's going to execute the instruction. So we flip the coins only once, and then we fix the result. We don't do this in real time, right? So we do it only once, and this is going to give us a single filter function. Okay, so that's again a single machine. How do I actually get many machines? All I have to do is repeat the process. So if I flip the coins once, that's going to give me one filter function, and that's going to give me a new machine. And if I flip the coins again, that's going to give me a second filter function, and it's also going to give me a second machine, and so on, right? So I can do this n factorial times. And that's how I built many machines out of basically a single shuffling machine. Okay, the problem now is that by allowing some machines not to execute some instructions, I basically introduce correlation among the machines. Like there's going to be machines that decide not to execute similar instructions. So that's going to make the machines correlated. And for proving a hardness result, it's important to show that the machines are uncorrelated. So how do we take these correlated machines now and make them uncorrelated, right? So that's going to be step 3. First of all, how do I measure correlation? briefly, I'm going to use the probability of agreement. So basically, that means that if I have two machines and I give them the same input, what's the probability that their output is the same? And I'm going to say the machines are uncorrelated if the probability of agreement is roughly uniform. And so the way that I'm going to achieve this result, again, the machines don't satisfy this property necessarily. So I want to make sure that the machines that I created satisfy this property. So the way that we're going to do this is by basically allowing, again, the machines to execute some instructions that have been rejected by the filter. So what we're going to do is we're going to create k copies, in particular n log n copies of each swap instruction. Okay, so what do I mean by that? So here's an example. So basically now the instruction 512 is going to be labeled. Previously we just had 512. Now we're going to label the instructions from 1 to k. And let's say this is the ith copy of this particular instruction, and the filter decides to execute it. And then we go to the next instruction, which is 3 and 10. So this is also labeled. And let's say this is the jth labeled copy of this instruction. The machine might decide not to execute this particular instruction. So how do we do this? Again, we have a set of instructions initially, n choose 2. And what we're going to do is we're going to copy this set of instructions k times. So now instead of having n choose 2 instructions, we're going to have k times n choose 2 instructions. And we're also going to flip coins for each copy of instructions. Okay, so how do we measure probability of agreement? So we're going to reduce the whole thing to a random walk. So the initial starting state, let's consider, for example, the deck of cards, is when the deck of cards haven't been shuffled at all, right? So here we have two machines, the left machine and the right machine, and they both start from the identity state. Again, think like the deck of cards haven't been shuffled at all. So what we're going to do is going to sample an instruction uniformly at random. So let's say we sample the instruction 3 and 10. And then depending on what the filter function is for each machine is going to decide if it's going to execute the instruction or not. In this particular case, the left machine, let's say it had heads, so it decides to execute the instruction, and that takes the machine to the step P310. So basically, P represents the permutation operation for 3 and 10. But the second machine, the right machine, had tails, so it doesn't execute the instruction, so it stays at the identity. And we repeat this again. We sample a new instruction uniformly at random. So let's say we got 5 and 12, and then we look at the coins again. Each machine looks at the coins. In this case, the left machine has tails, so it doesn't execute the instruction. The right machine has heads, so it is going to execute the instruction. And we keep doing this. And after these steps, we're going to measure the probability of agreement. Okay, so this is probably the most mathematical part of the lecture. Basically skipped all math in the paper or converted them to animations. So the probability of agreement is basically equal to the probability of being at a particular state of the two machines being at a particular state at step t, which we represent here by pt and pt prime. And then condition on this step, we measure the probability that the two machines have the same state, the same output. And then we have to sum over all possible states. Then what we're going to do is going to rewrite the condition probability as uniform plus some error. Remember, our goal is to show that the probability of agreement is roughly uniform. So we basically rewrite the condition probability here as uniform plus the error, and then we try to control the error. So using this equation, this simplifies to uniform plus this big sum is basically the whole error term. But this is basically it's just an inner product. So we can change notation to the inner product. So then we have uniform plus the inner product between the error and the probability mass function. And that's where it becomes technical. I'm not going to get into the details. Basically, we can show that the inner product of the two functions is equal to the inner product of their Fourier coefficients. And in fact, out of all these Fourier coefficients, only one is non-zero. And it's the one that corresponds to the standard representation of the permutation group Sn. Okay. So then the last step is basically to determine the magnitude of these coefficients. In fact, we can show that if you do enough iterations, if you do enough shuffling steps, let's say, in particular, if you do n squared log n steps, then the error part is tiny. It's going to be of the order 1 over n factorial, which is much smaller than the 1 over n. And this basically shows that the probability of agreement is roughly uniform. Okay, so how do I use the probability of agreement? Let me go back to the initial question. How do I identify the target F star? Well, I'm using the information from the oracle, and then I'm trying to eliminate machines that are not equal to the target F star. And the question is, how many machines can I eliminate per query? And this probability of agreement basically controls this quantity, right? So how many machines I can eliminate per query. This is a standard result. It's not our result. The elimination formula, the number of machines you can eliminate is given by this complicated formula. But if the probability of agreement is roughly uniform, then this formula eliminates to theta n over t squared. So let's interpret the result. So what does it mean? It means that, let's say t is fixed. So that means we can eliminate at most polynomially many machines per query. And we have exponentially many machines. So this implies super polynomially many queries in order to identify the target machine. The only way that we can make this the learner to learn fast by statistical queries is by allowing the tolerance to be exponentially small. But of course, this is going to imply that then you need exponential super polynomial time to actually run an algorithm. Okay, so that's the hardness result. Let's now go to the positive result. So this result is, on the other hand, previously we had end-to-end training. Now we're going to go into step-by-step training with the gradient descent. We're going to show that it's possible for a basic class of neural networks to learn exactly and efficiently. All right, so this theoretical work, so we're going to keep things simple. We're going to use a two-layer feed-forward network, and we're going to study this in the infinite width limit. So this is actually known as a known result from neural tangent kernel. And what we're going to do here, of course, this is not our work, of course. What we're going to do here is we're going to use this result in order to show that neural networks can learn to execute instructions exactly. All right, so let me give you an example. So the example is addition, and the algorithm is going to be the ripple carry adder. So we have two binary numbers, 1, 0 and 1, 1. And the first instruction is basically an addition instruction, but the instruction is bitwise. And so what we're going to do is we're going to take the first bit for each number, and we're going to add the two bits, and the result is going to be 0 and carry 1. And then we have to repeat the same instruction for the second bit, 0 and 1. So we add them together, and we get 1 and carry 0. And then the second instruction of the algorithm is carry propagation. So in this case, we don't have any carry to propagate, so we're just going to propagate 0, and that then that's the final result is 1, 0, 1. Okay, so this is a very simple case where basically the addition algorithm converges terminates in one iteration. All right, so I want a neural network to learn to execute this particular algorithm. So the first thing I have to do is find a way to represent the data. So what I'm going to do is I'm going to embed the data into a vector where its coordinate has a very particular interpretation. And the vector is going to have this block form that I'm showing here. So the first one is going to be a carry bit, and then we'll have the block of the first bits of its number. Then we're going to have another carry, and then the last block is the block of the second bits. Okay, so having this particular representation of the data, now I need to construct the training data, right? So what's my X, right? What's the data that I'm training my neural network on? So basically what we're going to do here is that for each block, I'm going to make sure that the model has seen all possible data that can happen for each block, right? Not all possible data that can happen, basically any possible, any combination of numbers that you want to add, right? We're focusing here on each block separately, and for each block, we have to see all possible cases. So if you take the block P2, Q2, there are four cases, 1, 1, 0, 1, 1, 0, and 0, 0. So we ignore the 0, 0 case, it's not useful. And for the carry, there's only two cases, 1 and 0. We ignore the 0 case again. Okay, so that's my X, basically, right? The input X. And it has this block structure. Now, what's the output Y, right? So basically, the output represents what's going to happen if we see a particular row in the input, what should be the corresponding output, right? So each row basically, as we'll see later, represents an instruction in the algorithm. Well, let me give you an example. Let's take the focus on the block P2, Q2, and let's say the model sees bits 1, 1. So then the model understands that it has to add those two bits, and the result should be carry 1, and everything else should be 0. And if we do the same for another row, 0, 1, then the model again understands that it should add a 0 and 1, and the result is 1, 0. And if we see a carry, then the model knows, based on the data, that it has to do a carry propagation. Okay, so basically what we are doing here is we are taking the algorithm, which has two instructions, bitwise sum and carry propagation, and we are converting those instructions into data. Those instructions represent the target function f, and we are converting these instructions into data. And then what we do is we take the data, we train a model, and then the model learns to execute those instructions, and we put the model in a loop with some additional rounding functions, and then the model is, we're going to show the model is able to execute the algorithm exactly without making any error and efficiently. Okay, so how do we begin proving such a result? When we train an algorithm, we basically usually we initialize the parameters randomly. So that basically makes the neural network, the output neural network after training, a random variable. And it's basically, we use here the known observation that the output model represented here by fx is basically Gaussian process. I'm not going to get into the details of this. But what I care about here is the mean behavior of this random variable and the standard deviation, the variance of the neural network as well. Okay, so the next slide is basically going to interpret what the mean is and what the variance is going to be. All right, so the mean is actually very useful. We can show that the mean is 100% correct. If we're going to train the model into data like I showed before, then we can show that the mean is going to be is going to execute the instructions correctly. And we focus here on some tasks like permutation, addition of binary numbers, multiplication, and even simulating one's instruction set computer. And the nice thing here is that we can show that the mean basically learns to execute this task exactly quite efficiently in the sense that the training data size is logarithmic in all possible inputs. Okay, but this is why does this make sense, right? So how do we achieve zero error? What we basically do is we overfit the training data, right? So, and you can think it like humans learn. If I give you a few instructions, then you have to make sure you execute the instructions correctly, right? You don't, you're not getting confused the instructions. So, and if you learn the instructions, then you, for every possible input to the algorithm, you'll be able to execute the instructions correctly. So what we do here is we overfit the training data, and that guarantees that the model has learned to execute the instructions correctly. And then that implies that it can execute the algorithm for all possible inputs. Okay, so here's how the addition works. Just very intuitively, at a very high level, after training, the model does pattern matching. So let's say we want to add those two numbers, 1, 0, and 1, 1. We're going to represent the data in this block vector form. And then what the model is going to do is going to look at each block. And let me give you an example. Let's say the model is going to look at block B2. It's going to check if it has seen this piece of data in its training data set. And it has, right? Because for every block, we make sure that the training data set includes all possible cases. So then the model knows that it has to execute a bitwise sum, and it does exactly that, right? It knows the output of this particular instruction as well. And then it's going to check another block, right? And it does this in parallel, actually. So it's going to check another block, let's say block B4. It's going to check if it has seen this particular data in its training data set, and it has, and then it knows it has to execute a bitwise sum. And then it takes all the outputs, adds them together, and this gives the correct output. In this particular case, the algorithm terminates in one iteration. Otherwise, we'll just loop over this process. Okay, so what about other tasks? We have some sufficient conditions. So the conditions basically say that if there's no correlation in the training data, if there's not much correlation in the training data among the instructions, then the model is not getting confused and it's able to execute its instruction correctly. And we also want the blocks to be order 1. So that basically means that we need to find a representation of the input data such that the blocks don't scale with some parameter. Okay, so if we have those two, then we can show that the model can learn the instructions. So if we put the learn model f hat, let's say, in a loop, then it's going to execute the algorithm correctly. And it's going to, again, do it. It's going to learn also efficiently, as I mentioned in the previous slide. Okay, so this was about the mean behavior, right? But in practice, we don't have access to the mean. We train maybe the data a few times, and then we try to do something with the trained models. In this particular case, we're going to take the trained models, and then we're going to average them. And what we care about is measuring how many models do we need to train, do we need to average, in order to guarantee with high probability that the averaged models can predict correctly without error. Can execute correctly without error the algorithm. So let me give you an example. Let's say our goal is to copy bits from input to output, and we need to copy k bits, right? And the sample size, the number of models that we need to train and average, is going to be m. So in this particular case, just for copying data from input to output, if you have 30 bits to copy from input to output, then we need to train about 300 models in order to guarantee 100% accuracy that the model is going to copy the data from input to output correctly with high probability. And each model actually can be very large, right? So the variance basically controls how many models we need to train, and if the variance is bad, it's actually we need to train a lot of models. What about other applications like permutation, addition, multiplication? Well, I've ordered here the applications in order of some intuitive complexity, and we can see here that even if we just want to permute the data and the input is 30 bits, in order to guarantee 100% accuracy with high probability, we need to train roughly 10,000 models. And what you see here, the two lines is numerical experiments and our theoretical result. And we kind of show that the theoretical result has the same rate. They're not the same because they are constants, and that's why they differ, but the rate is the same. What about addition? If we want to add two numbers where each number has 30 bits, then we need around 100,000 models. We need to train an average around 100,000 models to guarantee correctness. And multiplication, which is a slightly more complex algorithm, if we want to multiply two numbers where each number is 30 bits, then we need roughly 1,000 models. So in general, what we show is that the number of models that we need to train scales quadratically with input bits L. And what's important to note here is that these scaling plots, of course, they hold only for the particular data representation that I showed earlier, and the particular architecture, neural network architecture that I showed earlier. Somebody can find another representation or use other architecture, which is way more efficient. But this is an open question, actually. All right, so this brings me to the end of the talk, and thank you very much.